In 1990, the United States built 37 out of every 100 chips on Earth. Today, that number is 12. The other 88% now comes from a stretch of ocean that China has called, on the record, a renegade province it intends to reclaim. So somewhere in a boardroom in Seoul, and another one in Phoenix, and another one in Syracuse, New York, 3 companies looked at that map and made a combined bet of close to $300 billion that they could move the center of gravity of the most important industry on the planet back across the Pacific. This is the story of whether that bet actually works, starting with the one company brave enough or desperate enough to challenge TSMC head-on American soil at the most difficult node in the history of the chip industry. Samsung's plant in Taylor, Texas was supposed to cost $17 billion. It now costs somewhere between $37 and $44 billion, with internal filings suggesting the company is considering pushing past $50 billion and a long-term master plan on file with the state of Texas for up to 11 fabs and $192 billion in total investment. That is not a typo, and that is not a rounding error. That is a company trying to buy its way into a market that one rival already owns 65% of. So let's talk about what 65% actually means, because the number sounds abstract until you put it next to its competitor. TSMC controls between 65 and 68% of the global contract chip manufacturing market. Samsung Foundry, despite 3 decades in the business, sits at somewhere between 7 and 9%. That gap is not a rounding error either. That is the difference between being the rule maker and being a rule follower, and it is the single fact that explains every decision Samsung has made in Taylor since the shovels first hit the ground. Here's the part that should make you lean in though, because this is not just a story about money. It's a story about 2 companies racing toward the same physical cliff edge, using 2 completely different routes to get there. At 2 nanometers, the old way of building a transistor stops working. For decades, chipmakers used something called fin field effect transistors, where the gate that controls the flow of electricity wraps around the channel on 3 sides. That worked fine until you needed transistors so small that electrons started leaking through the channel even when the transistor was supposed to be off. The fix is called gate-all-around architecture, where the gate wraps around the channel on all 4 sides instead of 3, giving near-perfect control over when current flows and when it doesn't. Samsung adopted this gate-all-around design back in 2022 at its 3-nanometer node. TSMC, the company everyone assumes is years ahead on every metric, actually stuck with the old fin-based design all the way through its 3-nanometer generation and only switched to gate-all-around in late 2025 at 2 nanometers. That means Samsung has 3 extra years of real-world manufacturing data on a transistor architecture that TSMC is just now learning to use at scale. For the first time in over a decade, Samsung is not playing catch-up on the actual physics. It is playing catch-up on everything else. And everything else turns out to be doing a lot of damage. Look at the yield numbers, because this is where the story gets uncomfortable for Samsung fast. TSMC's 2-nanometer node is running at 70 to 80% yield, with a maturity target above 75%. Samsung's equivalent node, called SF2, is sitting at 55 to 60% yield on its best products. Now, yield sounds like a boring manufacturing statistic until you understand what it actually costs you in dollars per chip. So let's do that math together, because it's the single most important number in this entire story. Picture a single silicon wafer that can physically hold 500 individual chips, what the industry calls dies. If your manufacturing process is mature and you're hitting 90% yield, you walk away with 450 working chips from that wafer. Now run the same wafer through an early-stage 2-nanometer process at 55% yield, and you only get 275 working chips. Same wafer, same raw materials, same machines running around the clock. The difference is entirely in how many of those 500 chips actually work when you test them. Here's the twist nobody mentions in the headlines. Samsung is selling its 2-nanometer wafers for roughly $20,000 each, while TSMC charges around $30,000 for the same size wafer. Sounds like Samsung is the bargain option, right? Except once you divide the wafer price by the number of working chips you actually get out of it, Samsung's early 2nm process ends up costing about 80% more per chip than TSMC's mature process. Samsung's discount on paper turns into a premium in practice. That is the yield matrix, and it is the single biggest reason analysts are nervous about Taylor, Texas, no matter how many billions of dollars get poured into the ground there. So why is Samsung still doing this? Why pour $44 billion into a fab that, on the numbers alone, looks like it's losing the yield war before it even opens? Because Samsung isn't trying to win the same game TSMC is playing. It's trying to change what the game even is. TSMC runs what's called an open foundry model. You design your chip, you send it to TSMC to be fabricated, and then you send those finished chips somewhere else entirely for advanced packaging, usually to outsourced assembly and testing companies. Multiple companies, multiple shipping legs, multiple points where something can go wrong or get delayed. Samsung is offering something different, a vertically integrated, turnkey solution that bundles advanced logic manufacturing, high-bandwidth memory production, and advanced 2.5D and 3D packaging, all under one corporate roof, using Samsung's own iCube and xCube packaging platforms. For a hyperscaler trying to build an AI accelerator, that means one phone call instead of 4. One contract instead of 4, and one company to blame instead of 4 to chase down when something slips. That pitch is already landing. Tesla signed a $16.5 billion multi-year agreement running through 2033 to manufacture its next-generation AI-6 autonomous driving chip at Taylor. Apple has opened preliminary talks with Samsung to source custom silicon and advanced image sensors for the iPhone 18 lineup, part of a broader $100 billion domestic procurement push. These are not small commitments from companies known for being ruthless about supplier reliability. They are bets that Samsung's all-in-one model is worth the yield gap, at least for now. But timing is where the real tension lives, and this is the open loop that should worry anyone betting on Taylor in the short term. TSMC's first-generation 2nm node already entered high-volume production in the fourth quarter of 2025 at 2 separate fabs in Taiwan, both fully booked through 2026, with Apple alone holding over half of that initial capacity. Samsung's 2nm mass production at Taylor isn't scheduled to begin until 2027. That's a technology gap of roughly a year and a half to 2 years, in an industry where customers sign multi-year capacity commitments based on whoever can deliver first. And the macro backdrop explains why everyone is suddenly racing the clock at all. The United States government placed a 25% tariff on specific advanced semiconductor imports under Section 232 of the Trade Expansion Act, and modeling from the Information Technology and Innovation Foundation found that a broader, blanket 50% tariff on foreign-made chips would shave roughly 0.4% off U.S. GDP growth in year one alone, compounding to a cumulative loss of $4.4 trillion over a decade if left in place. Whether or not that tariff escalates further, the message to every fabless chip designer in America has already landed. Build a domestic backup plan now, or pay for not having one later. There's a second pressure cooker sitting right on top of the tariff story, and it's arguably more urgent. Advanced packaging is jammed. Demand for TSMC's chip-on wafer-on substrate packaging, the technology that lets you stack logic chips and memory chips into a single AI accelerator, is outstripping available capacity by 40 to 50%, with lead times stretching past a full year heading into 2026. That bottleneck alone has forced fabless companies who would never have considered a second foundry 5 years ago to actively go shopping for one now. Samsung's entire pitch in Taylor is built to catch exactly those customers as they walk out TSMC's door, frustrated and looking for an alternative. Now, none of this works without the single most expensive and most scarce piece of equipment in the entire semiconductor supply chain. And there is exactly one company on Earth that makes it. ASML, based in the Netherlands, is the sole manufacturer of extreme ultraviolet lithography machines, the tools that actually etch circuit patterns onto silicon at the nanometer scale. There are two tiers. Standard low numerical aperture machines cost around $200 million each and can print features down to 13 nanometers. The next generation high numerical aperture machines cost up to $400 million apiece and can resolve down to 8 nanometers, but lead times on those stretch 2 to 3 years from order to delivery. ASML closed out 2025 with a record order backlog of $38.8 billion, 65% of it extreme ultraviolet orders, against a global annual production capacity capped at somewhere between 70 and 80 machines a year. Every fab on Earth that wants to build at the leading edge is standing in the same line for the same handful of machines made by the same single company. This is also where you can see the philosophical split between the major players laid bare. Intel is going all in on the expensive, next-generation, high numerical aperture machines, installing the first commercial units to run its 18A node in Oregon and Arizona. TSMC has deliberately deferred high numerical aperture adoption all the way through 2029, betting that the cheaper, older machines combined with more complex multi-patterning techniques remain more cost-effective for now. Samsung, meanwhile, is running its initial 2-nanometer capacity at Taylor entirely on the cheaper, low numerical aperture scanners. 3 different companies, 3 different bets on which machine pays for itself fastest. And all 3 of them are betting hundreds of billions of dollars on being right. Even if Samsung gets every machine it needs on schedule, the physical plant itself has to behave like almost no other building on Earth. At 2 nanometers, a single nanometer of structural vibration can ruin an entire lot of wafers. So the Taylor facility is built on massive concrete waffle slabs that physically isolate the cleanroom floor from the mechanical pumps and chemical systems below it, holding ambient vibration below an industry threshold called VCD. The air itself has to meet ISO 14644 Class 3 and Class 4 standards, meaning fewer than 10 particles larger than 0.1 microns per cubic meter, filtered through continuous, high-efficiency particulate air and ultra-low penetration air systems running over 300 full air changes every single hour. And underneath the cleanroom floor, thousands of utility lines for ultra-pure water, vacuum systems, bulk nitrogen, and highly toxic process gases all have to be coordinated through building information modeling, so detailed that engineers call it Level of Development 400, the highest tier the industry uses. Then there's the resource bill that almost never makes it into the press releases. Taylor needs over 100 megawatts of continuous, uninterrupted power run through the Encore grid, which is tied to the ERCOT system, the same Texas grid infrastructure that has buckled under winter storms before. And at full operating capacity, the plant needs roughly 15 million gallons of water a day for ultra-pure water processing, most of it pulled from the Carrizo-Wilcox Aquifer through a dedicated pipeline project with an on-site reclamation facility designed to recycle 75% of that water back into the process. This is not a factory in the way most people picture a factory. It is closer to a small city's worth of infrastructure, dedicated entirely to keeping dust particles you cannot see with the naked eye away from a few square centimeters of silicon. And the cracks are already showing in the supply chain meant to support all of it. Solbrain, a South Korean chemical supplier that committed roughly $549 million to build a materials plant supporting Taylor, suspended that construction in late 2025, citing a sharp jump in U.S. construction costs and an inability to lock down firm order volumes from its own customers. Samsung's own foundry and system LSI divisions posted an estimated operating loss of 6.8 trillion South Korean won in 2025. And Samsung's 2-nanometer multi-project wafer test runs, the trial runs that validate the process for customers before mass production even begins, slipped 6 months from April to October of 2026 because of exactly the yield and process maturity issues we already walked through. There's a third player in this race that almost never makes the headlines because it isn't fighting for the same customers at all. Micron has pledged up to $100 billion over the next 2 decades to build a memory manufacturing hub near Syracuse, New York, aiming to capture up to 10% of global memory share. Micron isn't trying to out-yield TSMC on logic chips. It's making a separate, quieter bet that the same AI boom driving demand for advanced packaging is also driving an enormous, undercovered demand for high-bandwidth memory. The stacks of memory chips that sit right next to AI accelerators and feed them data fast enough to keep up. If Samsung's bet in Taylor is about replacing TSMC, Micron's bet in Syracuse is about making sure that whoever wins the logic war still has to come through American memory suppliers to finish the chip. $2 billion wagers on 2 completely different links of the same supply chain, both betting that the country that controls the most pieces of the puzzle ends up controlling the puzzle. And then there's Intel, the company everyone wrote off 5 years ago, and almost nobody is writing off anymore. Intel uses its own gate-all-around architecture called Ribbon FET, paired with a backside power delivery system it calls PowerVia, which is already active in production, while Samsung and TSMC are both still developing their own versions of backside power delivery. Intel's 18A node reportedly hit high-volume production after what insiders are calling a 5-year marathon back to relevance. And the company is the most aggressive of the 3 on adopting the expensive, next-generation high numerical aperture lithography tools, running them now in Oregon and Arizona. Intel doesn't have Samsung's yield problem or TSMC's order backlog. What it has is a 5-year credibility gap with customers who left for Taiwan and Korea the last time Intel promised a comeback and didn't deliver one. The 3-way race in 2-nanometer and below isn't actually a 2-horse race between Samsung and TSMC anymore. It's 3 different companies, 3 different transistor architectures, 3 different lithography bets, and 3 different theories of how you win back a market that consolidated down to 2 or 3 players over the last 2 decades. What ties all 3 of these projects together, and what nobody fully talks about, is the supply chain quietly building up underneath them in Central Texas specifically. South Korean materials suppliers are setting up shop right alongside Samsung, replicating their domestic supply chain piece by piece. Dongjin Semichem has committed an additional $110 million on top of its original $70 million investment in Texas chemical production. Fine Semitech secured a 25 billion won contract to supply extreme ultraviolet pellicle handling and thermal control equipment directly to the Taylor fab floor. Linde Gas runs its own dedicated air separation facility on the Taylor campus, piping high-purity nitrogen, argon, oxygen, and hydrogen straight into the fab. None of this shows up in the headline investment numbers, but all of it is the actual infrastructure that determines whether Taylor can run at full capacity or whether it spends its first few years of operation waiting on chemicals that were supposed to arrive 18 months earlier. A 2-nanometer fab is only as fast as its slowest supplier, and right now, at least one of those suppliers has already hit pause. So here is the actual verdict, and it comes down to one mechanism, not one opinion. Running a state-of-the-art 2-nanometer fab at low utilization is one of the most financially dangerous positions a chip company can be in, because the depreciation on those extreme ultraviolet machines keeps draining the balance sheet whether the fab is producing chips or not. If Samsung stabilizes its yields toward the 70% range and keeps stacking up anchor customers like Tesla and potentially Apple, Taylor becomes the proof that a serious vertically integrated alternative to TSMC can exist on American soil. And Central Texas becomes the second capital of the global chip industry, projected to pump up to $42 billion a year into the regional economy once fully operational. If the yield problems persist and the supplier base keeps fraying the way Solbrain just did, Taylor risks becoming the most expensive cautionary tale in the history of American industrial policy. A building that cost $44 billion to prove that some monopolies don't break just because you decide to compete with them. Either way, the next 18 months of yield reports out of Taylor will tell you more about the future of the global chip industry than any politician's speech ever will. Keep watching that number. It's the only one that actually matters.